So by now we have discussed about the pin description of 8051 microcontroller. In pin description we discussed that in microcontroller 8051 there are 4 ports and each port is having 8 pins. So in total there are 32 pins for these 4 ports. Now all of these ports can be used as input or output ports. Port 1 is exclusively designed for I/O purpose, connecting input or output device, whereas remaining 3 ports are having some dual function also. Now the value of these ports, means suppose if we are considering all the 8 pins of a port, then we can access all the 8 pins of the port at a time. For example, suppose if we write this instruction, move A, P0. So now the purpose of this instruction is whatever is there in port 0, all the 8 pins of port 0, that is P0.7 to P0.1, 0.0, all these pins. So this is our controller. So here basically this port is acting as input port. So we have connected some input device or some switches to this port. This is our port 0. So all the 8 bits, the value of 8 bits of port 0 will be moved to A register. So in this particular instruction, we are accessing all the 8 pins of port 0. So this is a instruction, byte addressable instruction. Basically we are accessing all the 8 bits. Now if in any application we want to access only one pin, suppose we want to access in port 0 at pin number 0.0, we have connected one LED. Suppose one LED we have connected and we want to glow this LED, we want to blink this LED, we want to make this LED on and we want to make this LED off. So in this case there is no need to access the remaining pins of port 0 because we have connected our LED only to one particular pin of port 0. So we require in this case to access only pin number 0 of port 0. So this can also be done. For example, in this case if we write instruction set B P0.0. So in this instruction the pin number 0, this indicates pin number and this indicates port. To indicate port and this is pin number. So port 0, pin number 0 will set. So this instruction will make this pin 1, that is plus 5 volt. So now this pin is 1, this is a LED. In this LED this is N terminal, this is P terminal and N terminal is connected to ground. And now at the P terminal we have generated 1. 1 indicates that is VCC plus 5 volt. So now P terminal is connected to plus 5 volt, N is connected to ground. So now this LED or this diode is forward biased. If the diode is forward biased, then current will flow through the diode. And since it is a LED, so when the current will start flowing through the diode, this LED will glow. And if you want to stop glowing this LED, then at the pin number 0 we have to generate binary 0, that is in place of plus 5 volt now we will generate 0 volt. So if E terminal is at 0 volt N terminal is permanently connected at 0 volt. So what will happen? P and N, both terminals are at same potential. And if they are in same potential, then LED will not forward biased and there will be no flow of the current, so LED will remain off. So in this way, now to generate this 0, we can write instruction CLR P 0.0. So in this case, we are accessing only one pin of port 0 and we are making that pin 0. So CLR means clear. That pin will be cleared. So these two are bit related instruction, right? With this we are accessing the bit of particular port, whereas this is byte addressable instruction where we are accessing all the 8 bits of the port. So for the all 4 ports, we can access any pin of all these 4 ports, or we can access in the ports in itself also. Okay, so now we will see, we will write one program to blink the LED. So we will write our for this circuit diagram we will write the program. Suppose this is our microcontroller 8051, and with this microcontroller I have connected now this one LED. This end is connected to plus 5 volt. So there is one resistance we have to use, and the value of this resistor we can use up to 220 ohm. So the purpose of this resistance is to limit the current which will flow through this LED, so that the LED should not burn out, to limit the current. Now this is LED. And suppose we have connected this LED to pin number port 1 and pin number 0. So now to make this LED off, now here what we have done, P terminal, this is P terminal of the LED and this is N terminal of the LED. The P terminal of the LED is permanently we have connected to plus 5 volt. Now depending upon the value of N terminal, if we want to make LED off, to make this LED off, P and N both terminal must be at the same potential. So what we will do, we will generate a 5 volt at pin number 1.0. So if here we will get 5 volt, then N terminal will be at 5 volt and P terminal is already connected at 5 volt. So both the terminals will be at same potential and LED will not glow. So we have to generate here plus 5 volt. Plus 5 volt in binary we represent by binary 1. So we have to generate here basically binary 1. To generate binary 1, what we have to do? We have to simply set this pin. If this pin will set means 1. It will generate 1. So to make LED off, P1.0 is at binary 1, and to make our LED on, we have to make this LED forward biased. For the forward biased, P is permanently connected to plus 5 volt. We have to connect this N terminal to 0 or ground. So now to connect this to ground or 0 volt, this pin number 1.0 should generate 0, binary 0. So to make our LED on, P1.0 is at 0. So now for making it pin number 1.0 at 0 means CLR P 1.0, and to make LED off P 1.0 is at 1. At 1 means here you have to generate 1. How we will generate? Set B P 1.0. So basically we will use set B P 1.0 and CLR P 1.0 to blink this LED. Now if we write the program in this way, org 0000H. So what we will do, first we will on this LED, right? So our operation is on, off, then on, off. So this will continue. This will continue till this controller is on. So first we will on this. So to on this, this is the option. We have to clear pin number 1.0. So we will write instruction CLR P 1.0. So now with this instruction, what will happen? Now after each instruction, while writing our program in the software, if you want to write the comment so that you can understand why we have written this instruction, that we can write. For that we have to just write here first, write here one semicolon. Write the semicolon. After that we can, whatever we will write, that will be the comment. So with this, what we are doing, with CLR P 1.0 we are making LED on. So we will write here on LED. And once the LED is on, now we have to off the LED. Now to off the LED, we have to write instruction set B P 1.0. So here set B P 1.0. So this instruction will make off LED. It will make LED off. So now LED is on and LED is off. This particular work has been done. Now again we have to on the LED. If again we have to on the LED, then again we have to write CLR P 1.0, and to off the LED again we have to write set B P 1.0. Now this task is completed. Now again we have to perform same task. So these set of instructions we have to write. For how many times? We don't know. For infinite times we have to write, because suppose our this controller is on for 1 day, 2 day, 3 day, or for continuously on. So it must have these instructions to on the LED, to off the LED. Continuously you have to write the instruction. So, but this is not the right process, because how many instructions we will write? So what we will do here, after performing this first task, only thing is we have to repeat this task. So how we can repeat? If here I write instruction S jump, that is short jump, repeat. So repeat is a label. So now with short jump, I will transfer the sequence of my program to label repeat. So repeat I will write here. Repeat. So now first LED will on. When we on our controller, our first instruction is CLR P 1.0 at code memory location 0000H. So controller will execute this instruction. This instruction will make your LED on. Then controller will execute this instruction set B P 1.0. It will make our LED off. After that, controller will execute this instruction S jump repeat. Now the sequence of program will go to label repeat. So now again controller will come to this point, and here CLR P 1.0. With this it will make LED on. Again set B P 1.0. It will make LED off. Then again S jump repeat. So now this program is in loop. So these 1, 2, 3, these three set of instructions will continuously executed by the microcontroller up to the period if your controller is on, then continuously these three instructions will be executed till our controller is on. Now in this program, LED will on and off, but now there is one problem. What is the problem? This instruction microcontroller executes in one machine cycle. So this instruction microcontroller executes in one machine cycle. This instruction also microcontroller executes in one machine cycle. So, and if suppose with this microcontroller, if we have connected a crystal of frequency 12 megahertz, then already in previous lectures we have already calculated that if the crystal of 12 megahertz is connected, then the time required for one machine cycle will be 1 microseconds. So now if when controller will execute CLR P 1.0, it will execute this instruction in one machine cycle. So after one machine cycle means after 1 microsecond this LED is on. Now LED is on. Now after this controller will execute this instruction. Now this instruction controller will execute in one machine cycle. So LED will remain on only for 1 microsecond, because after 1 microsecond this instruction has been executed, and this will make LED off. Now LED is off. Now again LED is off for 1 microsecond. So now what is happening? LED will on for 1 microsecond and LED will off for 1 microsecond. Now this 1 microsecond on and off blinking, we cannot see from our eyes this blinking of these LED for 1 microsecond. Now what we want to increase the on and off period. The LED should remain off for 10 seconds, just like in traffic light control, for 30 seconds or for 1 second. So, and LED is off for 5 seconds. Like that, we want to now just incorporate delay. So once the LED with these instructions, once we make LED on, now our controller should generate here some delay, right? Delay for some time. After that time only this instruction should be executed, and it will make your LED off. And once the LED is off, again controller should generate some delay. A delay can be of 100 millisecond, 1000 millisecond, 5 second, 10 second, 20 second, 1 hour, 2 hour, whatever it may be. So, but delay must be generated here. And after the delay, program will go back to repeat level, and again this instruction will be executed. It will make LED on. After that again delay will be generated. So now how to generate that delay? Now how we will generate delay? So basically there are two methods to generate delay. One approach is called as software approach, and another approach is hardware approach. Now in case of software approach, with the help of software, we will generate delay. Software means instructions. So whatever instructions we are writing, all these are the softwares. So with the help of instructions, we will generate delay. And in hardware approach, with the help of some hardware like timer, with the help of some timer, we will generate delay. So first we will see the software approach to generate delay. So delay generation using software approach. Now here, in one of the previous lecture, we just discussed about the machine cycle. So machine cycle is the time duration to execute one instruction. So now what we will do, we will use this concept of the machine cycle to generate delay. Suppose if I write one instruction here, move R0, comma, in this R0 register, suppose I am loading a value 250. So here I have written D. This indicates this is a decimal number. So 250 value we will load in R0 register. And basically, when we execute this instruction or when we assemble this instruction, at that time our assembler will convert this 250 decimal number into its equivalent hexadecimal number, and that hexadecimal number will actually load it in R0. But for the ease of programmer, the facility is there in the software that we can write this decimal number directly without converting it in hexadecimal. So now this instruction requires one machine cycle for the execution. So whenever we want to load some immediate value in any of these registers like R0, R1, R2, R3, then to perform this operation, to load 250 value in R0, our microcontroller require one machine cycle for complete execution. And we know the machine cycle. What is machine cycle? In one machine cycle, there are 12 T states. We are talking about 8051 microcontroller. So in one machine cycle, there are 12 T states. Now these are the clocks. These are clocks. So, and this is T state means one time period. This is 1 T state, and this is 2 T state. Like this, in total in one machine cycle there are 12 T state. And what is the timing? What is the duration of one T state? It is not fixed. But what is fixed? In one machine cycle there will be 12 T state. There cannot be 11 T state or there cannot be 13 T state. So what is the fixed thing? 12 T state will be there in one machine cycle. But what is the time duration of one T state? That is not fixed. That depends upon the crystal, external crystal which we have connected. If we have connected a crystal of 12 megahertz, then the T state, this T state, one T state will be of 1 microsecond. And if we have connected a crystal of 24 megahertz, then the same T state will become 0.5 microseconds, right? Because we have increased the frequency. We have doubled the frequency. If we will double the frequency, that time period will half. So in that case, it will this. So it depends upon what is the frequency of the crystal which we have connected to controller. Now let us assume that in our this particular application, our controller is having a crystal of frequency 12 megahertz. Now if the crystal is there for the frequency of 12 megahertz, then the one T state, one time period will be of 1 microsecond. And the time required to execute one machine cycle will be no. So total time required for one machine cycle will be 1 microsecond. In fact, this time period is 1 divided by 12 into 10 raised to the minus 6 second for the crystal of 12 megahertz. And in one machine cycle there are 12 T states. That's why we multiply this by 12. That's why we got 1 microsecond. 1 microsecond is the time period for one machine cycle. If the crystal is of 12 megahertz and if the crystal is of 24 megahertz, then the one machine cycle will become of 0.5 microsecond. Right? So one machine cycle is of 1 microsecond. So now to load 250 value in R0 register, our controller requires 1 microseconds. After this, if we write one instruction D, J, N, Z, R0, go to label B1, and B1 is suppose this label. Now to execute D, J and Z R0, this instruction microcontroller requires 2 machine cycles. Right? So you can find from the manual how many machine cycles are required for particular instruction. It is given in the manual. So for this instruction it requires 2 machine cycles. Now in R0 we are having 250 value. So first this instruction it will decrease the value of, if I will bring this label here only. So now first controller will execute this instruction. To execute this instruction, controller will require 1 machine cycle. Then controller will execute this instruction. It D, J and Z R0. It will decrease the value of R0 by 1. Now R0 will become 249. Now if the value of R0 is not 0, go back to label B1. So it is not 0 in this case, so again come back to same place, this label. And again controller will execute same instruction. So again it will decrease the value of R0 by 1. So now it will become 248. Now still it is not 0. Again go back to label B1. Again controller will come to this place and execute same instruction. So the same instruction will be executed for 250 times. Because in R0 we are having 250. And this instruction will require 250 execution to make the value of R0 0. So this instruction will be executed by the controller for 250 times. And for one execution of this instruction, controller requires 2 machine cycles. So in total, how many machine cycles controller will require to completely make this R0 0 by this instruction? So for that, for execution of one D, J and Z R0, controller will require 2 machine cycles, and this instruction is executed 250 times. Right? So now this will be how many machine cycles are required to execute both of these instructions completely. So this is 1 machine cycle plus 500 machine cycles. So this is 501 machine cycles. And we have connected a crystal of 12 megahertz. That's why for 12 megahertz, one machine cycle will be of 1 microsecond. So to completely execute these two instructions, microcontroller require 501 microseconds. So for this, 501 microsecond. So now controller will require 501 microsecond. And suppose, so these two sets of the instructions we can use to generate delay in our program. Now suppose we want to generate delay more than 501 microsecond. So if you want to suppose generate delay more than 501 microsecond, then what we have to do? Then in that case, in R0, what maximum value we can load? We can load, this is an 8-bit register, so maximum we can load 255D, that is FF. FF we can load in R0 register, and the decimal value of R0 FF is 255. So in R0, if we are having 255, then this instruction will be executed for 255 times. So in that case, the maximum delay this R0 will produce one machine cycle for this move R0 comma hash 250 plus this instruction will repeat for 250. Now here is suppose we are having 255. So this instruction will execute 255 times, and for each execution it requires 2 machine cycles. So 2 machine cycle multiplied by 250. 255. So 255 is 510 plus this 1. So this is 511 machine cycles, and which is equal to 511 microseconds. So with R0, with not only R0, R0, not R1, R2 or any register which is a 8-bit register, maximum we can generate 511 microsecond delay. Now if we want to generate delay of suppose 1000 microseconds, which is equal to 1 millisecond, then what we will do? So what we will do, so just now we discussed that with the value 250, we are generating a delay of 501 microsecond. We will neglect this 1 microsecond, because when we are talking about 500 microsecond, then if it is in place of 501, if it is 1, then also no problem. We can neglect this 1. So suppose this is 500 microsecond, we consider it as 500 microsecond. So these two set of instructions are generating 500 microsecond, and we want to generate 1 millisecond. So we know that 1 millisecond is equal to this 500 microsecond multiplied by, if you multiply it by 2, what you will get? 500 into 2 is 1000 microsecond, which is equal to 1 millisecond. So basically, if these set of instructions are repeated for 2 times, then we can get 1 millisecond of the delay. So how we can achieve that? For that, what we will do? We will use another register now. Move R1, in that I will load value 2D. Right. And here D, J and Z R1. I will decrease this. If R1 is not 0, go to label B2, and B2 is this label. Now you see what will happen. This instruction executes in 1 machine cycle, This is one machine cycle, this is two machine cycle, and D, G and Z, as I already told you, it requires two machine cycles. So now these set of instructions for move R0, comma hash 250, it require one machine cycle. For D, G and Z R0, comma B1, to execute this instruction once, we require two machine cycles. But this instruction is executing 250 times because in R0 we are having 250. So this we will multiply by 250. So here you just see what happened. This instruction will be executed 250 times. After 250 times of the execution, the value of R0 will become 0. Once the value of R0 will become 0, program will not go to the level B1. Program will not come here. It will come out from the loop. So now this instruction will be executed. So after 250 times, after the execution of 250 times, this instruction, program will come out from the loop because R0 has become 0. And now this instruction is executed. What this instruction will do? D, G and Z R1. It will decrease the value of R1 by 1. The value of R1 is 2. Now this R1 will become 1 because it will decrease the value of R1 by 1. So R1 will become 1. So R1 is 1. It is non-zero. Then program will go to level B2. And B2 is this. B2 is this. Again R0 will be loaded by 250. Then D, G and Z R0 B1. This instruction is executed. So again this instruction will be executed for 250 times. Right? This instruction executed once and this is executed for 250 times. Once the value of R0 will become 0, again program will come out from the loop. And now D, G and Z R1. So previously R1 was 1 and now D, G and Z R1, it will make R1 0. Now R1 is 0, program will not go to level B2. It will come out from the loop. So basically what is happening, due to this value 2 in R1 and due to this instruction D, G and Z R1 B2, these set of instructions are repeated 2 times. So what we will do, these set of instructions is repeated 2 times, right? And one machine cycle for this instruction. That also I will add one machine cycle. So these are total machine cycles which are required to execute this particular set of instructions. So how many machine cycles are there? 1. This is 1 plus 2 machine cycle into 250. So this will be 500 machine cycles multiplied by 2. So this will be here plus 1 machine cycle plus 501 multiplied by 2 times. So this will give you 501 machine cycle multiplied by 2, and this will be 1 machine cycle this plus 1002 machine cycles, and total 1003 machine cycles. So now these 1, 2, 3, 4 set of instructions with value 2 in R1 and 250 in R0 will generate will be executed in 103 machine cycles, and if the crystal frequency is 12 megahertz, then this will generate 1003 microseconds, right? So we approximate this, so this is equal to 1000 microsecond, and which is equal to 1 millisecond. So these set of instructions are giving us a delay of 1 millisecond, right? And if we increase this value R0, so these set of instructions, suppose here in place of 2D, if I put 10D, then what will happen? these set of instructions will execute 10 times. 10 times means here we put 10. So this I will put 10. So this is 5010 plus 1, 5011, 5011, 5011. So these many machine cycles, and it is equal to 5011 microseconds. So it is approximately equal to 5 milliseconds. So here if I put 10, then it will give us delay of 5 milliseconds. And if here I will put 100, so into 10, so it will give us the delay of 50 milliseconds. If I will put here 200, so double that, then it will give me the delay of 100 milliseconds. So like that, if we change the value of these resistors, it will change the delay. And we can use other resistors also. Suppose here we can use R2 also, R3 also, any resistors we can use. So by increasing the number of resistors, by increasing the value in these resistors, we can able to generate delay of longer duration of 10 seconds, 1 second, 5 seconds, 1 minute, 2 minutes, 10 minutes, even hours also, that we can generate. So here one thing, for previous set of for this set of instructions, these 4, where 2 is there in R1, 250 is there in R0. With these set of instructions, we are generating a delay of total machine cycle required are 1003. So basically, if simply we say 250 times this instruction is executing, for execution of this instruction we require 2 machine cycle, and 250 times we are executing this. So basically this instruction is giving us 500 machine cycles. And overall, again these set of instructions we are repeating 2 times. So overall, multiply by 2, so it will give us 1000 machine cycles. So roughly we can overlook the values, the machine cycles required for this instruction and this instruction, right? For these 2 instructions we can just overlook, because in place of 103 microsecond, 1003 microsecond, if we consider it as 1 microsecond, okay, it is very close to 103 microsecond. So these, what values we are loading in R1 and R0, these are called as overheads. To generate the delay, these are the overheads. We can neglect these values and directly we can calculate from here. 250 times we are executing this means 500 machine cycle, and that 500 machine cycle is again multiplied by 2, so 1000 machine cycles. So we can neglect these overhead delays. So this is about the software delay. So now in next lecture I will just use these instructions of the software delay in my main program of blinking of the LED, which in the starting I have discussed. Then we will see that LED will blink, will be on and off after certain duration.